So, at the beginning of the lecture, I would like just to highlight two key aspects that we forgot to mention about the matrix calculation for EIGRP before we move to link state protocols. So what we have mentioned is that when I calculate the matrix using the default mode, in which case K1 and K3 are set to 1, right? So for one link, like if I want to calculate the metric from R1 to R2, the metric is simply, so the metric will be, for this link, the delay is 20,000 microsecond and the bandwidth is 1544 kilobits per second. So as we said, the metric will be using the reference bandwidth 10 to the power 7 divided by the bandwidth of this link in kilobits per second, which is 1544. Okay, so this is the bandwidth, this is the metric between R1 to R2 plus the delay, right? And as we said, the delay is calculated based on the delay in microsecond, which is 20,000 divided by 10. So what we forgot to mention is that both numbers should be multiplied by 256. So that's one thing we forgot to mention, okay? So the matrix, so they have to be multiplied by 256. So this is one important thing we have to keep in mind, okay? So this is for the calculation of the metric on one link. The second thing is that if I want to calculate again the metric between R1 and the fast Ethernet. So the metric between R1 all the way to this LAN, not to the R2, but to the R2 LAN. In which case we have two hubs or two links, right? So we have to calculate the metric for this link first, and then for this LAN. So the way we do that, we have to keep in mind that there is a difference between the bandwidth and the delay. The bandwidth is, we call it a bottleneck parameter, which means that the bandwidth for us is like the thickness of the link or the thickness of the pipe. So if we want to calculate the cost related to the bandwidth for end-to-end links, we have to calculate it based on the bottleneck or based on the lowest bandwidth. Based on the lowest bandwidth. It's not accumulative. Okay? Only the delay is an accumulative parameter, in which case you have to calculate the delay for each link and get the summation of both. So that's one more thing that we have to keep in mind. We mentioned that before, but we did not highlight it when we tried to calculate the metric. In other words, the metric between R1 and the R2 LAN will have two components, the bandwidth component and the delay component, right? So for the bandwidth, we have to see which one is the lowest bandwidth. Okay, so in that case, this one is lower than this one, because this is like 10,000 and this is 1,500. Which means that this link will be the bottleneck for the end-to-end bandwidth calculation. In that case, we need to calculate the bandwidth part only for this link. Which means that the matrix has two parts, the bandwidth part and the delay part. For the bandwidth, it's simply 10 to the power 7 divided by 1544, okay, and we multiply that by 256. So that's the bandwidth part. So we don't do it for the two links, we do it only for the bottleneck link, okay. And then the delay part, which will be accumulative, and in that case it will be like 20,000 divided by 10 times 256 plus 100 divided by 10 times 256. Okay, so that's how we calculate. This is how we calculate the matrix. Okay, so again, the matrix has two parts: the delay part and the bandwidth part. For calculating the bandwidth, we have to calculate it based on the lowest bandwidth end to end, not accumulative. Any confusion? 256. Yeah, we said that this is the method of calculation. We forgot to say that last time, that you need to multiply all the numbers by 256, and that's why the matrix sometimes would be in the order of like 100,000 and things like that. So the metric is not like hop count 1, 2, 3. No, and it's not like when you when you receive the route updates from one router. The route update will have the separate values for bandwidth, delay, and so on. Okay? So we don't simply increment like the case of RIP. No, we have to take these numbers and calculate the end-to-end based on this method of calculation. So we have to say which bandwidth is lower, the incoming bandwidth or the one that I have, and calculate the bandwidth part of the matrix, and then take the delay and accumulate the part that's directly connected to this router, and then get the summation of both.
So it will choose the path depending on this calculation?
Yes.
But if the number was big, it will choose this path, or when the number is small?
No, in general, we have to, like in the route updates. The route updates are coming from the neighbors, right? So the neighbor is telling me that, be aware that I have this metric to this destination. Okay. So for example, router 2 will send router 1 some route updates for a specific destination, which is this Ethernet LAN, for example. Okay, so the metric to this Ethernet LAN will have two components. We'll have the bandwidth component and we'll have the delay component. And what normally happens, what normally gets communicated in the route update is the bandwidth and delay, those two values. Those two values will be communicated, right? So router 1 will say, okay, I have route information from router 2 is telling me that I can reach to this Ethernet LAN using the bandwidth and delay information like this. So do I have another route to this LAN? If the answer is yes, then you have to calculate this metric just as we did like this, and then you have to check the metric in the routing table that you have. If this metric is lower, then you replace it with the one that you have. If this metric is higher, then you ignore it. Okay? But this is the way that you have to, this is the way you use to calculate the metric end to end. For end to end, you have to be aware that bandwidth is a bottleneck parameter. It's not an accumulative parameter, like the delay. Because it represents like a thickness of the pipe. Right? So if you want to flow some fluid end to end, your limit will be the smallest one, which means in our case the lowest bandwidth. Right? So this is the bandwidth part of the metric. But the delay is actually the delay you encounter on this link plus the delay you encounter on this link plus the delay you encounter on this link and so on. So the delay is accumulative, but the bandwidth is a bottleneck parameter. Okay? That's why these values, they get actually communicated in the route update separately. And if you go back to the message format of EIGRP, you will find that these values, you don't actually send a metric. You send these values separately. Okay? So you you use these values to calculate the metric and then compare it with the one that you have. If it's better, insert it. If it's worse, ignore it. That's how you should do it. Okay? So that's a missing part based on what we have discussed. The link state routing protocols, we said that we use Dijkstra algorithm, which is in fact a centralized way of calculating the best route. So if router 2 wants to reach to the LAN of router 3, then it has many paths to go, right? So it has to calculate the cost for each of these potential or alternative path, and then finds the one with the That's why we called it shortest path first algorithm, or shortest path first protocols. Okay, so if you calculate the cost going this way or the cost going this way, you will find it higher.
So we're looking at the distance or the cost?
The cost, and the cost here we have to accumulate the cost on each link simply. Okay, and we have to do that again in a centralized way. It's not anymore like we receive a route update from this, and then we check. No, we have all the information about all these links at the root, at this node here. So all these, the topological paths are known to each individual router. Okay? So each individual router will then construct, as we will discuss, will construct what we call shortest path tree. So if router 2 wants to reach to this LAN, it needs to go through this route. If it wants to go to this LAN, it needs to go to this route. And the shortest path here is not necessarily the lowest number of hops, right? Because some links here have double the cost compared to other links. So you may actually end up going through a longer route in terms of the number of hops, but this will give you the shortest path in terms of cost. Okay?
This cost is calculated by the router?
We'll see, because now we're talking about link state routing protocols in general. We did not talk about specific protocol like EIGRP. For link state, we will study OSPF, right? So we will study how OSPF calculates this cost in a more or less similar way like EIGRP, except that we will see that some slight differences here. But this is an abstract way. If you have the cost like this, and we deal with link state routing protocol, then you have to construct all possible paths from one node to all the possible destinations, which means that you have to have global information about the topology of the network, okay, at every individual node. So simply the shortest path gets constructed from each individual node. So for example, the router 2 will have router 2 LAN from router 1 to router 2 with a cost of 22, which is where is that? Yeah, from router 1. So this is the table for router 1, right? So if I want from router 1 to reach to router 2 LAN, I have to go this way and this way with a cost of 22, which is 20 plus 2. If I want to go to router 3 LAN, so I have to go this way and then this way, which is 5 plus 2 is 7, and so on. So this is what we call the shortest path tree. It gets actually formulated as a table, and each router will formulate this shortest path tree. But before this step, there is a prerequisite step that has to happen, which we will discuss in a minute. You don't just generate this shortest path table directly. You have to have some. You have to gather some information first. We'll see how that happens. So this is what we call shortest path first tree for router 1. Okay. So link state routing process describes how routers use the link state routing to reach conversions. So here the process is fundamentally different compared to the distant vector protocols. So we'll see the steps. The steps here are very important to understand compared to distant vector routing protocols. So the first thing is that each router will learn about its directly connected links. And this step is similar to distant vector routing protocols. Each router will also automatically get the information about the directly connected links, whether it's a serial point-to-point, or if it's a LAN, it knows that this LAN is, for example, fast Ethernet, and the bandwidth is like so, and the delay is like so, and so on. So each router will simply get the information about the directly connected links. The second thing is also similar to EIGRP, not with RIP, because RIP does not use hello packets, but the link state routers will exchange hello packets to meet each other, which means that similar to EIGRP, the routers here will exchange hello packets to discover the adjacencies or the neighbors. Okay? And when I say the neighbor here, the neighbor is defined as the node or the router that I have one hop connection to, and this router happens to use the same routing protocol. Because if one router sends hello packet to another router, and this router happens to use a different routing protocol, this router will not send back any acknowledgement saying that yes, indeed, I'm using that routing protocol. The other router will not understand this hello packet because it does not use the same routing protocol. Because even though we're talking about hello packets, but the format of the hello packets and the information inside this hello packet is different when we talk about link state routing protocol or when we talk about EIGRP. Okay? So two routers use different routing protocols, they will not be able to exchange information together. So that's very important. So the purpose of the hello packet is to discover adjacencies, and when we talk about adjacencies, we mean actually the neighboring routers that use the same routing protocol. And if we talk about EIGRP, then we actually need one more extra information. The router that uses EIGRP using the same Huh? Using the same process ID. Right? Because we said that we could have multiple instances of EIGRP running in the network. Right? So each instance of this EIGRP will have different process ID. In which case, the neighbors are defined to be the nodes that use EIGRP using the same process ID. Otherwise, they are not neighbors. Okay? So that's the second step. The third step, each router builds its own link state packet. So starting from here, it gets totally different. So the first two steps, they have some similarity with EIGRP especially. Okay? I personally consider EIGRP somewhere in between. It's not really a totally distant vector routing protocol. And it's not link state routing protocol for sure. Right? So starting from here, it gets totally different. So the link state packet is a very important aspect for link state routing protocols, where each router needs to generate information about the directly connected links. Okay? And it needs to communicate the information about this directly connected links in terms of, okay, this link is like a serial point-to-point, or this is a LAN, this is an Ethernet, and the bandwidth of this link is like so. Okay? So someone might ask, okay, so the route information in EIGRP is similar, so I also send information about the link, and I also send bandwidth, and not only that, I send delay and so on. Right? So what is the difference between the route updates in EIGRP and the link state packet that we talk about here? There is a big difference. So the link state packets are sent in a flooding fashion. Okay? So the router collects information from the directly connected links, generates what we call a link state packet, and then it floods it all over the network. Not to the neighbors. The neighbors will actually rebroadcast these link state packets to all the routers in the network. That's why we call it flooding. Link state flooding. Okay? So the route update from distant vector routing protocol, it gets broadcast to the neighbors only. But here the link state packets will get flooded to the entire network. Right? And this happens in this step here. Once all routers have received the link state packets, they will collect all these link states in what we call link state table, which did not exist at all for distant vector routing protocol. In which case, each router will have the link state for all the links in the network. Okay? This is the first step for calculating the best route. Okay? So that's the sequence. When all the routers have all the link states in the for all the links in the network, we can consider that conversions have been achieved. That's it. So the conversions here happens when all the routers have all the link states for all the links in the network at every individual router. That's it. So conversions have been attained. Unlike for distant vector routing protocol, we have to do that gradually on multiple steps. So the first step is that when the router collects information about the directly connected links, it sends it to the neighbors. The neighbors will then have to process. We'll have to process this routing information and update the routing table accordingly. And then after some time, when the time comes, if we talk about periodic updates, then the information from the routing table will get collected and then sent to the neighbors. So in order for us to have a conversions, we have to have all these steps propagating in the entire network. And this is usually slower because in each step you have to do what? You have to send information and you have to process. Send, process, send, process. Okay? But here we talk about flooding. So we flood the link states in all the entire network without processing anything. فاهمين الفرق؟ Okay? So that's why the conversions can be attained here much faster. Because we don't have to do any processing in the middle. We just flood the information in the network. And we just make sure that all the routers get all the information. That's it. Without any processing. The processing using Dijkstra will happen in one shot at every individual router. In a centralized way. Because once you have all the information, خلاص, you can calculate the best routes based on constructing the shortest path tree using the Dijkstra algorithm. Yeah, there is intensive processing on each node, but it happens only once. Okay? Unlike for distant vector routing protocols, for every single route update, you have to update and you have to do some processing. Update your routing table, get the information from the routing table, send it to the neighbors. Neighbors will process, update the routing table, collect the information from the routing table, send it to the neighbors, and so on. Okay? So, so the link state routing protocols, this is the way that the router will gather all the information about the directly connected links. And the information are the IP address of the network and the type of this network, whether this is like a LAN or this is like a serial point-to-point network and so on. And of course the cost, or in our case mainly the bandwidth. Okay, so these are the links, and the link state will have the information about each link. This is the first step we talked about. The second step is that we have to recognize or discover the neighbors, in which case we have to use the hello packets. The hello packets are sent to the neighbors. Hello packets are sent similar to EIGRP. One hop broadcast, that's it. I want to discover the neighbors only. Okay? So the purpose of this protocol is just to discover the neighbors. And the neighbors here that use the same link state routing protocol. This is very important. Because if the neighboring router uses EIGRP, it's not neighbor. Okay? We talked about. The third step is when we send the hello packets, we send it in this way. So the router will send one hop broadcast to all the routers, and then the routers will reply as unicast, similar to EIGRP. One hop broadcast, and then receive the reply in a unicast fashion. So this will act as a keep alive mechanism, or as long as I receive reply from a specific router telling me that I'm here, I'm using the same routing protocol like you, then I put this in the adjacency table or the neighbors table, as that's a recognized or a discovered neighbor. Okay. So once I discover all the neighbors, then now I have to form what we call the link state packet, and the link state packet will have the information like here. So the link state packet, I want to maximize it like so. So the link state packet will have from router 1 will have information about all the directly connected links. So router 1 here has 1, 2, 3, 4. The first one is the LAN part. and then to router 2, and then to router 3, and then to router 4. So this is what we call the link state packet. So one link state packet will have information about all the directly connected links. So once I do that, then the link state packet will include all the information about the directly connected links and just flood this link state packet to the entire network. So the step of flooding here is very important. So what is the advantage and disadvantage of flooding? So the advantage of flooding is that we can reach the conversions very fast, right? Because I'm trying to send the information about the entire network to all the nodes, in which case the conversions will be attained very fast. Exactly. So this is the disadvantage. So the initial bandwidth required for flooding is high, right? So the initial bandwidth required for flooding is high. Luckily, we don't have to do flooding periodically. Okay? So as part of the link state mechanism, the link state packet exchange mechanism, the routers will recognize when to stop, because flooding can go forever, right? So when do I have to stop? There is a criteria based on which the routers will stop. Basically, when they receive link state flooding from a node, they broadcast it to all the nodes except the one it came from. And they keep doing that until they reach to a state that they get link state packets from all the neighbors, and there is no one to send it to, in which case they stop. So the flooding here is also controlled. So they stop. Once they stop, okay, they don't flood any more information except when a change happens. So only if there is a change in the network, the router that's directly connected to the link that has a change will again form the link state packet and will flood it to the network. Okay? So it only happens at the beginning and then when any change happens. So it's event based or triggered, similar to EIGRP. But the main difference here is that the link state packet gets flooded into the entire network, which again, it causes some initial bandwidth overhead. However, it speeds up the conversions. So again, the rule is each router will rebroadcast the link state packet to all the links except the one it came from. Okay, so that's the main rule. Okay, so so for example, the flooding here happens from router 1. Router 1 will send it to router 2, router 3, router 4. Okay, router 2, will send it only to router 5, right? Because this link state packet has been received from this link, so I will not send it back. Okay? Similarly, router 2 here, router 2, I think, router 2 will send it to this link only. Okay? Not to this link. Because this link is where the link state packet came from, so I will not send it back. And so router 4 here will actually receive 2 link state packets which are identical. So it may happen that a router will receive 2 identical link state packets. That's not a problem. This is the overhead of flooding. But in that case, router 4 will send the link state packet only to to 5 because it received this link state packet from here and it received it from here. Right? So it will send it only to router 5. Router 5 will say, okay, I received this from here, I received this from here, so I don't have to send it anymore. So it will stop. So flooding will not go forever in that case. So there is a stage that I reach and then I stop flooding. So in that case, I'm sure that the information about the directly connected links with router 1 have reached all the routers in the network. Each router will have to do the same. And this happens initially, and the flooding will happen in a similar way until all the routers have all the information about all the entire links. In which case, so in that case, I form what we call a link state database or a link state table. So this table will have information about all the links in the network. So router 1, in that case, will have information about this link, this link, this link, and all the links. Okay? And initially, I will store all this information in a table. This table is called link state database or link state table. From this table, I run the Dijkstra algorithm once to form what we call a shortest path tree. Shortest path tree at every individual node will tell me, okay, if you want to reach to this destination, you have to go this way. If you want to reach to this destination, you have to go this way. So the processing happens only in one shot for the entire network. Okay? From the shortest path tree, I will update the routing table accordingly. Also in one shot. So this is how the link state database looks like. So first, this is the link state database, which collects basically all the link state packets and store it in the table. So I received from router 1, for example, received from router 2 link state packet, and this link state packet contains this information. And from router 3, I received link state packet, and it contains this information. So it puts it in a table like this, and then it goes through it, and it removes all the duplicate links. For example, router 1 received from router 2 information about this link. But router 1 already knows this link, right? So it removes. This is a duplicate information, so I will not take it. So it removes this duplicate information, and then it runs Dijkstra algorithm to generate the shortest path tree. The shortest path tree, it tells me if you want to go to router 2 LAN, you have to go through router 2, and the coast would be like so. If you want to go to router 3 LAN, you have to go through router 3, and this is the coast, and so on. So this is the shortest path tree, which is the result or the outcome of running Dijkstra algorithm on this table. Okay? Any confusion? So you collect this information, you put it in a table. Dijkstra algorithm will run against this table, will form this table, and this table will go to the routing table. Okay? And from people, so it's not encouraging. I still feel that some of you are still confused. So that's how the shortest path tree gets constructed. So as we said, the shortest path first tree will get constructed from this table. Basically, what happens is that the router will go through every individual link state packet, and then it tries to process the information coming from this router. So, for example, the the router 1 will receive the link state packet from router 2, which contains information about the directly connected links. So I will have to go through each one, and then router 1 here ignores the first link state packet, which contains information about this link. Why? Because the reason is router 1 already knows its directly connected link. Router 1 already has this link as directly connected link. So it already knows about it. In which case, router 1 will ignore this link state information. But if you go to the second and third one, you'll find that this information for the LAN and information about this link. So router 1 does not have this information, in which case it will keep it and use it. Okay?
A table, and then each router will calculate the tree.
Right.
So there's no broadcasting
In the middle, once we reach to the conversion state, all the link state information will be collected by every individual router in the network. Okay? So every individual router individually will run the Dijkstra algorithm against the link state table to generate the shortest path tree. Okay? Independently بقى خلاص. I don't need any more information from any other routers. Okay? Only if there is a network change, one link goes down, one link goes up, things like that, then the directly connected router will collect information about this change and again will flood it. Only once. That's it. So again, router 2 will use the second link state packet. Why? Because router 1 uses the second link state packet, because this packet is about this LAN, and router 1 does not know about this LAN, so it will keep it. And so on. So I keep doing that, which means that basically I just need to remove all the duplicate information. Any link state information that is coming for a link that I already know about, I will remove it. I will ignore it. That's it. I will keep doing this, of course. I will keep doing this step by step. So router 1 uses the third link state packet, because again it's for a link that it does not know about, so it will keep it, and so on until I reach to a state that okay, that I clean the table, I clean the link state information table from all the duplicate links. In that case, I run the Dijkstra algorithm just once, in one shot. And the Dijkstra algorithm will parse all the link state information and create for me what we call a shortest path tree. So it tells me, okay, if you want to go to this destination, you have to go through this next hub, and the coast will be like so, and so on. So this is basically the shortest path tree. So once the shortest path, first algorithm has determined the shortest path routes, these routes are placed in the routing table. So the shortest path tree will get then inserted in the shortest path, in the routing table. Okay, so this is the routing table, which is the final outcome of running all the steps that we have gone through. So this table again has been formed in one shot by running the Dijkstra algorithm against the link state table. Totally unlike EIGRP, where EIGRP has to form this table gradually in multiple steps, hub by hub, and so on. And in every step you have to do processing. You have to do part of the processing, in which case, as we said, EIGRP uses a different algorithm. It does not use Dijkstra, it uses I don't think anyone will remember, but it uses another algorithm called Bellman-Ford. Bellman-Ford algorithm is the distributed algorithm is in nature. Okay? At the end, the outcome of both algorithms, by the way, should give you the same result. Okay? So the shortest path for EIGRP, if we were to use the bandwidth component, and OSPF, you should get to the same result, but the steps or the methodology was different. Okay, but the net outcome should be the same. And because the methodology is different, there is some advantages and disadvantages to each one of them, which we will talk about now. So based on that, based on the methodology, this comparison is very important. So when we talk about distant vector routing protocol, here we mean mainly RIP. Because as we said, EIGRP is not purely distant vector routing, because it uses, for example, triggered updates. It uses bounded updates, partial updates, and so on. But when we talk about distant vector routing protocols here, we mean essentially RIP, which is purely a distant vector routing protocol. So based on that, as we said, if we take the criterion of building topological map, this means that the router for distant vector routing protocol does not actually build any topological map, because RIP does not use any hello packets. It does not actually know the end-to-end topology, right? Because it does not have any global information. It uses only local information, in which case it does not have topological map, like link state routing protocol that has to construct this. A route can independently determine the shortest path to every network independently in one shot. Of course, this happens for link state, not for distant vector, where each router is dependent on all the neighbors to receive the routing information. Conversions, of course, is very slow for distant vector routing protocols compared to link state. As we said, collecting the link state happens in one shot by flooding, and this happens very fast. Of course, it will consume bandwidth at the beginning, but it will reach conversions very fast. And then, in terms of periodic updates, periodic event-driven routing updates, of course, the distant vector routing protocols are generally periodic. Generally periodic, right? We said the exception is EIGRP that uses a triggered updates and bounded updates. But in general, distant vector routing protocols are periodic, whereas the link state are generally triggered updates. Okay? So we collect information at the beginning, and then only when the change happens, we exchange link state packets. And of course, the use of link state packets happen for the link state routing protocols only. For distant vector routing protocols, we use the distance information. So that's a quick comparison between the two. Okay, so we'll stop here.